Hello, I'm Necmettin. Welcome to my fourth Omnet video for the computer networks lecture. And in this video, I'm going to explain the whole wireless tutorial, which consists of 14 steps. And I hope I'll do my best for explaining all of the steps. So sit back, relax, and enjoy. That's all I can say right now. I also took so many notes just in case because there are so many information, so many things that I have to explain. So I took some notes just in case. Sometimes I can see the notes because uh, I can't remember all of these all of these stuff. So let's start from our first step, which is the config wireless 01. This is the first step our tutorial, and we are directly connecting to our net file, which is called wireless A. That net file will consist of two hosts. This is a wireless area, by the way. We're gonna use the radio medium on here. Uh, when we examine the statements on here, our simulation time limit is 20 seconds, and we are going to use the global ARP for the mapping the MAC addresses to IP addresses, and for the sender, which is host A, we are going to use the application UDP basic app. The host A will send UDP packets to host B, and the destination it will use the destination port 5000, and the packet length, the message length, it says, it's also, you can say, the packet length, the data length, etc., will be the 1000 bytes. And on this specific statement called send interval, the host A will try to send packets to host B in random time intervals. When we take the mean value of these times, we will get 12 milliseconds, and also we will call these packets UDP data. Uh, Subsequently, the host A will send the packets to host B, and we will name these packets as UDP data 1, UDP data 2, UDP data 3, and so on. And let me check let me check something. Sorry for that. Yes, thank you. I had to check something, and for the host B, we are going to use UDP sync on the local port 5000. We are using UDP sync for the ignoring the packets that comes from the that come from the host A. When host B receives the packets from host A, it will automatically ignore and drop the packets. And for the wireless local area network settings for the all hosts, we also add some hacking wireless interface. I assume this for the acknowledgement messages. We created some base structure for the upcoming steps, because all of the steps are inheriting from the wireless 01, like wireless 02 inherits from the wireless 01, and wireless 02 inherits from the wireless 02, and so on. And the communication range will be 500 meters, and the distance between the host A and the host B is, I assume it was 400 meters. Let me check the values in the net file. Yes, it's 400 meters. So that means that they can directly communicate each other. Host A can send packets to host B, and host B can receive all of the packets. And the header length is 23 bytes, etc. So on. Let me start the simulation. And yeah, you can see the uh, first step. And let me start it. You can see the received packages uh, on the counter on the upper right side. uh, Let me make it slower a bit. You can see the packets as the UDP data 19, UDP data 20. It goes like that, and I wanna make it faster and reach to time limit, which is 20 seconds. And I'm going to close. And for the wireless 01, you can see the wireless 01 on here. This is the previous result, by the way, but they are the same because there are no specific topology changes. They are uh, all the same scenario. So I may keep until the wireless 3. I also, maybe after this first step, I'm gonna delete this wireless 2 and wireless 3 results for the making a bit uh, curious, surprising maybe. And I wanna search for the uh, let me search the packet packet sent packet sent count. So you can see only the host A's uh, values on here because the only sender is here is host A, and you can't see host B's. You can't see the value for the host B because it's only receiver, not sender. And let me search for the also package receive packet received count, and you can see there is only host B for these results because the only receiver is the host B, and I guess they are the same values, which is 1600 packets. The host A sent 1600 packets to host B, and the host B received all of the packets. There is no packet drops. It's obvious. I want to save it, and I want to delete the wireless 2 and wireless 3's results for making it a bit surprising. But they will all be the same. And let's get our second step, which is setting up some animations. This step is all about making make taking this first step into a fancier look with the animations. We will see some arrows. That dotted arrows will represent the possible routes. And let me check my note as well. When an arrow appears between the hosts, that means that the transmission is completed. So host A is succeeded to send packet to host B for each packet. And let me start the second step. You can see it's the same one with the first step, uh, but you will able to see the animations just like that. The host A will sending signals to host B, and host B is receiving this signals and receiving the packets. Yeah, you can see the arrows. Yeah, in the next steps, these dotted arrows will mean the possible routes, but for this step, it means that there is a successful transmission between host A and the host B. Host B received the packet, and the arrow will appear like this. I want to conclude it as well, and let's check our result. Here's the scalar result. That it's the same with the previous one, but I also want to see the packet sent and the packet received. You can see it's again 1600 packets. Host A sent these packets, and the host B is also received 1600 packets. Just like that. You can see the results on here. And let me check the wireless tree. For the wireless tree, we are going to add intermediate nodes for the making them act like routers. I'll call them routers. By the way, we also in the wireless tree we are connected to net file wireless B on here. You can see the intermediate routes as well. But we haven't configured the routing table yet, and from the first step the host A will try to communicate directly with the host B, and so but we also decrease the communication range to 250 meters for the old hosts, and also for the host R1 we also will show the communication range for the host R1. We activated it. Yeah, the distance between the host A and the host B is 400 meters, but because of the decrement of communication range, they can't directly communicate each other, but also the lack of the routing configuration. There will be no package receiving for the host B, but host A will send the packages, but host B won't receive the packages. The host R1 and the host R2 are in the suitable places for forwarding the packet to host B, but just like I said, we haven't configured the routing table, so there will be no packet receiving for the host B. So let me start the simulation for the wireless tree. Host R1 will drop the packets, by the way, because we haven't configured the routing yet. So you can see we activated the communication range for the host R1 as well, and I'm going to start the simulation. By the way, let me check the host A's routing table. Not like that. It was like this. I want to check it from the routing table, and so you can see there is no gateway. It will directly try to communicate with the host B. So you can see there is no packet receiving for the host B. You can see the counter on here, it's still 0. I'm going to conclude it because it's no use to make it lasting. I'm going to close it, and I wanna examine the results. And here, firstly, I wanna check the received packet for the host B. Packet received count. Let's see it. And you can see there is a big 0 on here because there is no packet receiving for all hosts. The only host that sent the packet is host A, but no one got packet receiving, so there is no data on this chart. I also want to check the package sending on here, package sent, and you can see the only host that tried to send packages is host A. It's like 1655 packages, but none of them are received by some particular host. So this is the end of the wireless 3. I want to save it as well. And let's get our wireless 4, which is it's a bit complicated. We're gonna activate the static routing for this wireless. We also change the routing table of the host A. I'm going to demonstrate it in the simulation guide. We make the static routing related to uh, error rate metric parameter. We also activated the forwarding on here. This means that we're gonna use the host R1 as a router. The host R2 is the suitable place as well, but we set the host R1 for acting like router. We also modified our visualizer settings for the step 4. That means that uh, we will see some giant colored arrows that represents the success of the packet transmission between host A and the host B, but there will be no more dotted arrows. That dotted arrows will still remain, but they are just representing the possible routes for the accessible routes for the host A and the host B. I assume. Let me check my paper as well because it's complicated a bit. The route will remain unchanged. Yeah, because of this static configuration, the route will remain same until the end of the simulation. Uh, we're also gonna configure visualization for seeing the paths that packets take when traveling from host A to host B, and the error rate will be so high. Like we set the error rate value to 1. It's defaultly configured, by the way, to value 1 outside of the communication range, and the routing will be created based on packet error rate of links between nodes, like I mentioned previously. And I also explained the cyan colored arrows means successful data exchange between the host two data link layers from the host A and the host B, two hosts. And let me execute the wireless 4 as well. Yeah, in this step we configured our XML file just like on here. This is the XML. It's not directly connected to a XML file, but it's the values inside of the XML format. Let me start it. Yeah, I started to. Yeah, you can see the host R1 also activated. Yeah, you can see that giant colored arrow. That means that there is a successful data exchange between host A and the host B through the host R1, because right now host R1 is acting like a router between the host A and the host B. The packet received is 3. You can see from the counter. We haven't configured the host R2 and the host RT for the packet transmission because of the link error rates, I assume. But I also want to show the host A. No, not for the error rate. I want to see the routing table. Yeah. Also, we also set our parameters related to error rate, but on this routing table for the host A, you can see we are using gateway 10.0.0.3. Uh, this line is representing between the data exchange between the host A and the host R1, not exchange. It's just when the data is received by the host R1, the data is forwarded by the host R1 to host B destination. You can see the IP address of the host B as well. This IP address is for the host B, I assume. We haven't configured the IP addresses for the visualization. It's hard to say. And let me open this again. The packet received 26. I want to conclude the simulation. You can see the cyan colored the arrow, the successful data exchange. Yes, we reached our simulation, and let's see our result on here. Here are the results for the wireless 4, and here's the charts for the host A and the host B, and we can clearly see that the quantity of the packet that are sent by host A is double to received packets by host B. There is a major difference. That's because of the according to tutorial, it says the host R1's network interface controller operates in an half duplex mode. It means that the host can't receive packets and send packets simultaneously. Yeah, it can receive packets and send packets in any time, but not both. Due to this case, that's the result of the wireless phone. For the step 5, we will take the interference into account, and let me explain the interference. Two signals or more signals can conflict each other when they arrive to destination in the same time. So that new signal, it's like a parasite. It's an unwanted thing for the device. So we set the interference range into 500 meters, and also we set the ignore interference option to false. That means that we take the interference into account, and we also set the we activated to display interference range. Also, we also made some change for the visualizer. I can say the visualize visualizer. How was it? Sorry for that. I need to see its pronunciation.
Visualizer.
Visualizer. Okay. Uh, for the data link layer, I assume for the data link layer access, maybe we turned off the data link visualization. So let me execute the wireless 5 as well. So you can see here's the red circle. It represents the interference range. So I'm going to start the simulation. There was a successful exchange between the host A and the host B. Let me speed up. And let me check the previous one's INI file as well for the red dot. Data link visualizer packet filter. Yeah, it's not the same. Okay, I want to speed up this. You can see the counter on here, but you can see the it's so low, the quantity of the received packets because of the interference. Host A is sending the data rapidly, and it causes the interference. So host B cannot get this data in a wanted form, in a appropriate form. Let me check this. Okay, then I have to check something. I wanna conclude the simulation. So the received packets are 138, which is really low, and I wanna see this results, and let's see the packet received count. So for the host B, the quantity of the received packets are 138, and when we see the packet sent on here, packet sent count, and you can see the package that are sent by host A is 1651, but there is a huge difference between the received packets and the sent packets because of the interference of the signals. So it's a big major for this step. We have to get rid of the interference in some kind of way, and I assume in the upcoming steps we're gonna take care of for the interference. Let me share this, and let's get the wireless 6, which is on here, and I have to check something as well. And this step is about using the CSMA configuration. We are going to try to reduce the collision of signals, the interference, with using the MAC protocol, but it's not related with the MAC address. The MAC protocol is called a medium access control protocol. So in the previous step, nodes were sharing packets without checking ongoing transmission, like that link is full, or that link is that link has a traffic, or etc. So that's why we had collisions and packet losses in the previous step, because the nodes weren't checking the state of the links. So we are going to try to prevent the collisions with using the CSMA protocol with the uh, carrier sense multiple access. That's the acronym of the carrier sense multiple access. The CSMA is the acronym of that. So this protocol is using the listen before talk principle. So it checks the state of the link before sending packets to that link. It checks I assume, the absence of the traffic on that link. So when we see the CSMA protocol properties as well, in the CSMA protocol, node has to verify the absence of the traffic in that link, like I just mentioned. So for this, we are going to use the CSMA's CA property. The CA is for the CA is acronym of the collision avoidance. This for to prevent the collisions, the interferences. So in this protocol, the node that has data will wait the absence of the traffic. Then it will wait a random backoff period, and it will wait that period for sending the packet. So if the channel is still idle mode, that means that traffic is absent. So it will try to send packets into that link, into that route, into that channel, whatever you say. So the node can start to transmission process with the if it's in the idle mode. So otherwise the procedure starts over with a possible update range for the backup period, I assume. It's waiting a time like, imagine that 5 seconds, but it's failed, so it's assigning a random number like 10 seconds, and so on. So the procedure will arrange for backup. We will also improve the throughput with that protocol. We are gonna also use the acknowledgement timeout. I assume on here acknowledgement timeout, which is 300 microseconds, and we also use the drop tail queue, and we also use the radio called unit disk radio, which is the simplest radio for this simulation. I guess in the step 14 and the step 13, I assume we are changing uh, the radio as well. So the queue type for the wireless interface is drop tail queue. It will discard the packets when queue is full as well. But you can see that the packet capacity is -1. That means that uh, besides of this drop tail queue statement, it can hold infinite number of the packets in a queue. So there is no limitation for the holding the packets in a queue because of the value of -1. Sorry for that, by the way. My eyes burn because of uh, I was on the computer so long, so that's why my eyes are burning right now. So useless because yes, I also mentioned it as well. So that's the it's finished. I assume for the uh, wireless step 6. So let me see the step 7. I wanna prepare the step 7 uh, as well. Yeah, uh, here's the page of the step 7 as well. Okay, so let me start the step 6. So for that, my eyes are still burning. So step 6, and let me start the simulation. uh, so this time, like I said, we are using the CSMA protocol with the collision, uh, with the property of the collision avoidance. So I'm going to start it, make it a bit slow. Yeah, because of the acknowledgement messages, I assume we also can see the host A may receive the packets according to acknowledgements as well. I assume in this step or other steps, there is a case like that happens. Host A receiving acknowledgement messages. I wanna make it faster, by the way. You can see the giant arrow for representing the successful data exchange. Yeah, I can see the acknowledgement messages as well for the host A because the arrow is also indicating host A. I want to conclude the simulation. So we finished our simulation, and I want to check the results. So waiting for the scalar. And yes, let me see the package receipt for the. I want to check the hostage receive packets. Is that happened? I'm curious about it. Received packet received, and so host. No, it's not happening in this configuration. Maybe upcoming configurations. There's no acknowledgement messages, I assume. Let me check this as well again. The INI file host 6 Q can hold acknowledgement messages. But it's not that case. It's not happening in the step 6. It's for the wireless 7. Sorry for that. Make use acknowledgements. I mixed up, but I'm gonna mention the acknowledgement messages in the wireless 7 as well. But for the step 6, it's not the case. We won't receive uh, packets for the host A. So I'm I want to check the host B, and it's 1069 packages. And for the package sent that are sent by the package sent count, and it's for the host A, it's 1618 packages. uh, I guess it's still about the maybe the half duplex, for the R1, the network interface controller, or there's still interference, but in a minor level. uh, that's all I can make it uh, I can say about this results. I want to change this as well, and let's get the wireless 7. I already explained the wireless 7 a bit. We are going to use the acknowledgement messages for the CSMA protocol. Uh, when the receiver will send acknowledgement messages to sender when the data exchange is successful. So host B will send acknowledgement messages to host A in the wireless 7, and let's start the simulation for the host 7 again. So let's start it, and I want to see the acknowledgement message for once, and after that I'm going to conclude the simulation. Yeah, host B is sending the acknowledgement message to host A. Okay, I'm going to conclude the simulation. So let's check the results of the wireless 7, because this time we are able to see the receipt packets that are for the host A as well. And I want to firstly check the packet received count for the host A as well. So, here's the host B, but I assume for this chart, for the UDP UDP app, we are only able to see the host B, but we have to know that host B also sending packages to host A, the acknowledgement messages. So, is there anything about the acknowledgement? Let me see that. Egg. package send count. Let's see the package send count. Host A sent 1656 and the host B got 1047 packages. And for the, let me check the tutorial. No, not this one. That's for the IPv configuration. Sorry. Steps for the step 7. Yeah, in this type of charts, we opened the wrong chart, I assume, but it's okay. So I wanna get the steps 8 because it's really time consuming right now. So in the wireless 8, it's about the setting modeling energy consumption. This time in this step we are going to work with the energy consumption and we are going to add components to node so we can model and measure their energy consumption, and we have to for this property we have to add some another statements like you can see on here. There are some properties, some statements about the consumption of energy. So for the simplicity we will ignore energy constraints like limitations, and we will ignore the uh, like battery capacities, etc., and we will install infinite energy sources into the node so they will work with the infinite energy. So there are so many statements on here. And let me check this, and let me check something again on my phone. Sometimes I mix up the word because it's so long. Yeah, we are supposing we are using the infinite energy sources for the devices. So I need to explain maybe some of them, like energy consumer type name in here. Uh, in here, we are using the state-based energy consumer. For the wireless interface, the energy consumption model depends on the radio state, like the state of idle, receiving, transmitting, etc. So, for the off-power consumption, we can see the power consumption when the radio is off. So, in the sleep power consumption, when the device when the sleep power consumption when it's in the sleep state, it's consuming 1 milliwatt. So switching power consumption, it's the power consumption while it's switching states, like maybe idle to receiving, it's 1 milliwatt as well. And let me see the another things like of power switching, the energy storage. The energy, there is a thing called energy storage type name. Yeah, ideal EP energy storage. It's about the installing the infinite energy sources to all hosts. Uh, the ideal in this model energy storage capacity is unlimited. It's full. So let me check the other things as well. Uh, I forgot to making it muted. Sorry for that. So for the radio display interference range, disables the display of the interference range. For the wireless interfaces, it's about the visualizer as well. We close the we closed the interference range. It's here, by the way. I was looking for the wrong place. So R1 display communication range. We closed the communication range of the host R1 as well. Uh, and the visualizer, medium visualizer display signals disables the display of signals in the medium visualizer. Let me check the properties again. Sorry for that. Uh, this step is real long. So I took so many notes and there are so many informations about it. Disables the display of signals in the medium visualizer. Okay, that's it. Let's start our step 8. Yeah, let's check it. So you can see there is only a circle which represents the communication range for the host A. So I'm going to start it. So I concluded the simulation for the host 8. It's about the power consumption and I want to see things about the power consumption as well. And but I don't know how to find it. Maybe I can write something like power, energy, display energy storage filter, consumption, maybe, or power consumption vector. So we opened our chart on here. So there are so many data. So I might also check the tutorial on here chart residual capacity vector. Residual capacity. Let's check the residual capacity then. Is it vector by the way? Vector. So here's the data about the consumption. So it's about the host A energy storage. Host A consumed its most of the energy. Host A is consumed its energy because uh, it's it's performing the most of the task that receiving the package, but in but rapidly. But we installed the CSMA protocol, but so we can see that host A consumed so much energy because we can see the energy storage chart on here. Host B, host R1, yeah. Also host R1 and the also host R1 also consumed the energy so much, but we can see that host B, host R2, and the host R3 consumed less energy than host A and the host R1 because host A sending package and the host R1 forwarding the packages because they are doing the most of the tasks. So it was like that. And let's get the step 9, which is on here. I also wanna prepare my page for the host 9 as well. There are so many things about these last steps. So for the host, for the wireless 9, it's about the configuring node movements. So in this step, uh, we are giving the we are giving nodes to mobility. They will able to go to north, I assume. So middle hosts will leave the communication range. uh, the host R2 and the host R3 may be used for the packet transmission for forwarding the packet to host B, but we haven't configured it yet. In statically, we are still using the host R1 for the host A routing table, but we need AODV protocol for the we need AODV protocol for the using host R2 and host R3 because in statically we can't use the host R2 and the host R3 yet. We have to wait the AODV protocol. So in the statically, uh, it's when the host R1 uh, leaves the communication range of host A and the host B. So there will be no package receiving for the host B. Host A will try to send packages uh, rapidly as well, but there will be no received packages for the host B. So I want to start the simulation again for the wireless 9. So you can see we gave mobility to intermediate routers, the intermediate hosts. I will call them routers again, just like I mentioned, because they are acting like routers. So then we start our simulation. It's slowly moving, by the way. You can check here slowly, and I want to make it faster. So host R1 will leave the communication range. So we also concluded our simulation. So then we see our results as well. Packet sent count. So we can see host A sent again 1664 and host B received only 548 packages. The main reason of the lack of the received packages is the host R1 left the communication range of the host A and the host B. Mainly host A, the communication range of the host A. So I want to save it as well. And let's get the wireless 10, which I also want to prepare my page for the host 10. Uh, step 10, sorry. So step 10 on here. So on the step 10, this time we are finally configuring ad hoc routing, ad hoc demand vector. That's the acronym of the AODV. Uh, AODV is the acronym of that, I assume. Let me check this out again. Ad hoc on demand distance vector routing. The AODV is the acronym of that word. Uh, so the root this routing protocol adapts the changing network topology. It creates the links, the paths, the route routes dynamically related to this protocol. So we are going to able to use R2 and R3 this time. Thanks for the AODV. So because of the AODV, routing tables are driven by demand. So dynamically, for AODV, we only need IP addresses. We don't need static routing like XML file. With using the AODV, we will able to use the links between the uh, which uses host A and the host R2 and the host A and the host R3, the paths which pass through host R3 and the host R2. So when the link is broken on the route to R1, because they are still mobilized, we gave the movement to them. So it is detected by the lack of the acknowledgement messages. So we are also using the acknowledgement messages as well. It's the inheritance from the uh, what was this? The CSMA protocol on the wireless 7. So AOD will create new routes for the that passes through host R2 and the host R3. So I wanna start the simulation again. There are still four more steps for this tutorial, by the way. So I opened the step 10. So you can see these intermediate routers will go to north, and when the host R1 will exceed to communication range of host A, the because of the AODV protocol, host A will send packages to host R2, and host R2 will send packages to host R3, and host R3 will send the package of the host B, and you will see about that. So you can see they are moving slowly, by the way. So a data exchange happened on here. I am curious about, did we close the movement? No, we are still using the movements. So yes, I want to make it a bit slower. Wait a bit. So you can clearly see that this time we are using host R2 and the host R3 for forwarding the packet to host B, because host R1 exceeded the communication range. So when we check our results again, and let me check the AODV for the which type they are using. It's not examining the results, by the way, but I wanna examine the results just in case. So packet send count. So let's see the package sent. We sent, the host A sent 1576. So let me browse the data for the package receive. So for the package received, you can see there is no host A, by the way, but you can see the host A as the UDP. It's, I guess it's about the creating the creating the routes related to AODV, I assume. Let me check the INI file again. By the way, my program was crashed a minute ago, so I restarted it. I stopped the video. So yes, it might be the property of the AODV, because in the AODV they are sending the messages, the routers sending messages each other. So as a acknowledgement for, it was like a hello message in the, I can say the as an example in AIGRP the routers are sending hello messages. It might be, it might be like that, I assume. So host B is here, host R1, host R2 on the host R3 on here as well. You can see the results on here. uh, Host R2 on the host R3 received more packages than the host R1. Here we can see the just nine packages to host A. It's a property of the AODV, just like I mentioned, like the acknowledgement messages for creating the routes between the routers and the hosts. So let's get the step 11. So I also rendering some video for the previous video. I stopped the video, so I'm gonna make them a whole. I guess there are three videos right now, so I have to render them. There is a lot of work, so uh, it's okay, by the way. So let's start step 11, which in this step we're also going to consider the obstacles, like in this configuration we are going to add an obstacle like a concrete wall on in front of the host A and the R1 and the R2, I assume. And we also going to connect the network wireless C, this net file you can see. I'm still waiting for the net file. We added the physical environment on here. You can think there is a concrete wall in front of the host A and between the host R1 and the host R2. They are still moving, by the way, to north. So when uh, when they are getting in front of the concrete wall, the communication between the host A and the intermediate routes are cut off. So because of the AODV, host A will try to communicate with the host R2, and the host R2 will communicate with the host R3. So let me see my notes as well simultaneously. So we also added the z-axis to, we are considering the height of the devices like 1.7 meters, like you are carrying a phone. You can consider like that. So the concrete wall is an obstacle, so it will absorb all of the signals. There is no such signal can go through the that obstacle. So because of that, there will be no connection unless we move to intermediate host node. We are going to define our concrete wall with the net file and the XML file as well. You can see the XML file on here. The material is concrete. Here is the properties of the concrete wall as well. We can examine. So with the parameter ideal obstacle loss on here, you can see obstacle will absorb all of the signals because of this property. Let's start the simulation. Waiting the INI file for the starting the simulation. Like I said, my application was crashed, so we're gonna wait a bit. Oh, we already configured. We have two simulations for that. Step 11. So you can see the concrete wall on here. In first, host A will connect to host R2, so it will send the packet through the host R2 and the host R3 to host B. And after host R2 and host R3 move behind of the concrete wall, host A will try to communicate with the host R1, and host R1 will forward the packet to host B because of the AODV protocol as well. So let's start the simulation and make it a bit faster. So in first, host A will uh, communicate with the host R2 on the host R3. We can see the Gian arrow after some time passed. Okay. Yeah, host R2 using host R1, by the way. I was mistaken. We are not using host R3. Host R2 is connected to host R1. Yeah, it's dynamic. It's changing time to time because of the AODV. The topology changes. I wanna make it a bit faster. So on here, it's directly connecting to host R1 because host A cannot connect to host R2 on the host R3 because of the concrete wall. Concrete wall absorbs all of the signals completely. So you can see the giant arrow. So on here, uh, when the host R1 uh, leaves the communication range, because of the AODV protocol, host A tried to connect uh, host R2 and host R2 tried to connect to host R3. Yeah, the path is created between these four devices, so host A would able to send packets to host B. So let's close the simulation. I accidentally opened another simulation. So let me check the results again. I hope I won't get any another crashes. And I'm curious which result type they are using. They are not showing the results, so I wanna still see the packet received. So on here, host A received some packets because of the it's in the UDP, by the way. Host B received most of the packets, the application and the UDP. You can also see the R1, host R2, and the host R3 quantity of the received packets because of the yeah, it's about the AODV, I assume. Still about the AODV. So package sent count as well. Let's check the package count. So for the package sent, you can see uh, host A sent the most of the packages, but we also can see there are some minority packages that are sent by host B, host R1, R2, and the R3 because of the uh, AODV as well. So that's the result of the step 11 about the obstacles. So when we get the wireless 12, which is the changing to more a realistic radio model. Uh, so simply we are changing our radio model to more realistic one. So in the beginning we are using what was that? We were using unit disc radio model, which was the simplest one. We were ignoring the signal attenuation, etc. So in this step, we're gonna use APS-key scalar radio medium. This we're gonna use this model as a radio, so we will able to simulate signal attenuations, and we will able to simulate signal uh, uh, obstacles, maybe obstacle loss, and APS K means amplitude and phase shifting keying. There are so many informations about it, by the way. Also, we need to specify carrier frequency, signal bandwidth, and transmission power. This for using the APS-key radio medium. We have to define these properties. So with the APS-key scalar radio, which on here we add physical layer header as well. And together with other parameters, it is possible to compute the path loss, bit errors rate, etc. And there is also another term called SNIR, which is on here. That means the signal, noise, and the interference. It's a ratio, by the way, and you can see the thresholds on here. There are so many thresholds. So on here, on the signal representing the suitable wanted signals. So noise is like the parasite, which is unwanted disturbances coming from the other devices, like noise or maybe other vibrations which conflicted with the signal, etc. And the interference, like I mentioned previously, conflicting two or more signals when they are arriving at destination at the same time. it's representing by the interference in the SNIR. So we also set the physical parameters to receiver uh, as well. You can see this is the this is for the transmitters, like the center frequency, bandwidth, etc. We also added the background noise power, which is minus 90 decibel. I assume this is the unit of this. So and we can see the center frequency as well, which is the 2 gigahertz. So about the receiver part, like sensitivity like this is the if the signal power is below this threshold reception, which is the minus 85 decibels. I assume I don't know the exact unit, but I assume they might be decibels. So under this threshold, the reception process is not possible. The data sending is not possible. Uh, I mean, the sender can send its data, but receiver can't receive the data uh, because of this threshold, which if it's below this threshold. So the also we have the energy detection on here, which has the same value with the sensitivity. So if the power of reception is below uh, this threshold, no signal is detected uh, by the receiver. It's also important for the receiving the signals. Uh, it determines the power of the signal. So and for the SNIR, the ratio of the signal noise and interference, there might be a specific value which is the 4 decibel for the SNIR threshold. Uh, if it's below for this value, so it means that there is no successful reception. So we can also see the bit error rate, etc. And let me start the simulation for the step 12. For the step 12, let me check the yes, okay, step 12. So it's the nearly the same, but we we changed our radio model this time. So let me start our simulation. By the way, right now it took 3 hours to making this video, and we still have two steps. It's so long. It's really so long. My application crashed 2 times. I also my video recorder also crashed. So there are 5 separate videos. So uh, I have to make them a whole. So when we make the faster, it's nearly the same, but there are some changes, which is according to previous steps. So let's see our results, like packet drop and the packet sent again, packet received and the packet sent. I cannot see the packet drop. I don't know. So host A on here, this is the received. Host A received packages as well because of the AODV. So you can see the other intermediate hosts as well, other routers. Quantity of the received packages are 316 for the host B. So let me check the package sent as well. So for this host A, we sent uh, 1782 packets, but because we implemented a more realistic uh, radio in this in the step 12. So because of this, in this case, the efficiency really dropped when we compare with the previous steps. So we are talking about the host A sent 1782 packets, and look at the number of the received packets, 316. So that's real low. So when we get the wireless 13 on here, let me check the 13 as well on here. So in this step, we're gonna also configure a more accurate path loss model, which is the by default the medium was using the free space path loss model, which assumes the line of sight path for the signals, and there will be no obstacles cause collisions in this model. So, but this time we will use two-ray ground reflection model to making the signals reflecting from the ground. So we also gonna add flat ground on here, you can see, and the ground elevation, the ground will be the 0 meters, which is the same level with the uh, ocean. So the height of the ground will be the 0 meters, like it's like the x-axis. So we also activated the two-ray ground reflection on here on this statement. So we also this time we will use the two-ray ground reflection to make calculates with that calculates with one reflection from the ground. We also consider the reflection from the ground, so signals can be reflected from the ground. So at first, the free space model and the two-ray ground reflection will have the same bit error when we start our simulation. But after that, maybe after the right before the host A exceeding the range of the communication range, we can see minor, not minor, the major differences between the uh, two-ray ground reflection and the what was that, the free space path loss. So when we see our simulation on here, let me start the simulation. So our simulation on here. So here's the schema, as you can see. So I wanna start it as well, and let me check the type of the result on here. So they are examining the bit rate, bit error rate for this step. So we will do the same. So let me make it a bit faster. They are still moving to north, by the way, the intermediate routers. We just seen the we just saw a successful data exchange between host A and host B. And we have seen. Let me make it a bit faster. So we concluded our simulation. So when we see the result for the wireless 13, what was that? Bit error rate vector. So I guess I was supposed to open the vector one. Let me save this, and I'm going to open the. Also need to save this. Bit error rate vector. So let me zoom it vertically on here. Zoom in, zoom in. So you can see that it's not in the suitable shape, by the way. But how do they make this? On the time, 5 seconds between the 11 seconds. Let me find it on here. 5 seconds and yes, just like that. One more. I can't observe the results. I don't know why they are not in the suitable shape, just like this one. I do not know why about the R1 as well, but you can see the chart on here. When we add the uh, more accurate path loss model, like we change the medium, uh, like we changed from free space path loss to uh, what was that, two-ray ground reflection model. You can see the two-ray ground reflection model's error rate will be higher than the free space path loss because of the reflections. And this time interval is about the time that right before the host R1 leaving the communication range of the host A and the host B. So this time interval includes this case, and you can see the results. It will be similar like that. So when we close this, let's get our last step finally, which is the step 14, the last page on my on here, and let me see it. And this time for this step we are gonna also consider the antenna gain. There is a term called antenna gain about the uh, in the previous steps the we were assuming the antenna gain in 0 decibels in the simulation and the configuration, but we are going to set the antenna gain to 3 decibels for improving the simulation. It's about the term antenna gain is for the improving the simulation and the power of the signals. Just like in the previous steps, we can we were able to make the reception in maybe 3 hops, like host host A to host R2 on the host R1 and the host B, which is the uh, one hop, two hop, three hops. But thanks for the antenna gain this time, we may able to conclude the receptions in two hops, which is the host A to host R1 and the host R1 to host B, or maybe when the host R1 moves to behind of the concrete wall, this time host A will try to communicate with the host R2, and because of the antenna gain, host R2 may able to communicate directly with the host B because of the increment because of the increment of the power of the signals due to antenna gain. So I'm checking which another properties, like till the end of the simulation R1 is in the communication range of the host A, and when R1 is left from the host A's communication range at the very end of the simulation, host A will send the packets to host B with the route through the R2, just like I mentioned previously. So in the just two hops, and let's see the simulation for the INI file, the step 14, and this is the last step, hopefully, because right now it's 12:36 a.m. and I started to record this video at 9 p.m. So let's start the simulation. So you can see host A, host R2 and the host B is communicating each other because of the antenna gain, the increment of the power of the signal. So we are able to see this case. So when we conclude our simulation, this time we reach the time limitation, which is the 20 seconds. And when we see our results, and let me see, is there any results for this? So there's no results. When we see the same things like packet received, host A, host B, host R1 and the host R2, they are nearly the same. When we see the package sent, it's nearly the same with the wireless 13. So that's the result of the uh, wireless 14. So that was the last step of this wireless tutorial, and so thanks for watching. We finally finished this tutorial, and it took me 3 hours to record this. So I hope I hope this video is good for you, and thanks for watching.